Awesome. Thank you, Somaya, and thanks everybody for joining us today. My name is Milena Rangelov, and I am with Vital Metrics right now, and this work has been done under Federal Highway Administration Sustainable Pavements Program. I also want to highlight my colleague, Michelle Helsel, who is here in row number 3. So she is joining me today, and we will be available to answer your questions from this domain. As Ali has mentioned already, a lot of this work has been done under Federal Highway Administration and LCA Pave tool, a lot of efforts on sustainability front. And today I want to talk a little bit about different types of decarbonization strategies we have seen and analyzed through our work. Just a little segue here. My presentation focuses on materials and it focuses on embodied carbon. Embodied carbon is the carbon that is contained in our materials and pavement designs, as opposed to operational carbon that's associated with vehicles driving on the roads. I know there is a controversy, it's like which one matters more, and why are we even focusing on embodied carbon? So there are a couple of reasons for that. Reason number one is that in terms of climate change mitigation, actions that we can do right now matter a lot more than actions we can do 10, 20, 30 years down the line. And that's your embodied carbon. That's how you construct your project to begin with. Second reason is that unlike operational emissions, embodied carbon cannot change once you are done with your project. So there's nothing you can do. Whereas if you change vehicle fleet down the line, let's say you electrify your vehicles, those operational emissions can drop quite significantly. And third reason is that so far we have seen substantial investments in clean electricity and vehicle electrification. Federal Highway does a lot of work on providing broader availability on vehicle electrification, charging stations, and so on. So we have many, many efforts on operational front. It's not that we have forgotten about that. It's just that we are focusing on what we as pavement engineers can influence through our work. All of that being said, this table here summarizes a series of strategies for concrete. We're not focusing on cement, just concrete here, that can be done to reduce embodied carbon of concrete. So here we have on the left-hand side the strategy, what is its readiness level for implementation, and where does it fall under carbon management hierarchy in terms of reducing emissions, replacing intensive constituents with something lighter, or offsetting our emissions and removing them. We also have life cycle phase, so does it happen early in the process or later in the process? As I mentioned, very important for the reversal of climate change. Economic indicators, does it cost us money? Does it save us money? And then the stakeholders, who are the decision makers holding the key to make these changes happen? So here in this graph, we have identified two that I want to talk about today. Because we have identified them as highly suitable, and that would be material efficient design through mixed design optimization. It's extremely ready. We know how to do it. These are very certain reductions that happen because we reduce materials that are we using rather than hoping that these changes will happen in the future. They are focused on material production phase and they help us save the money. They're also impacted by concrete producers like concrete industry as well as state DOTs, so we know the people who can actually bring these changes to life. The second one is material substitution through different types of supplementary cementitious materials, which is something you guys are probably familiar with. This was a very long first slide, so thank you for bearing with me. Okay, I will show you two studies that we have done, and these two studies are summarized in two of our papers. Papers are published, so you can find them, you can read them, cite them, you name it. So this research has been out for a while. This first presentation, I believe, has been seen by some of you here in the room. The second one is a little bit newer. So here we're talking about the effects of mixed design, and this was FHWA's study on paving concrete. We have done that with our friends from MCTC, Mobile Concrete Technology Center, and that is, as you can see here in this picture, our mobile concrete lab that travels all across the country and is the guest at different paving sites. So they have over the years crossed US back and forth a couple of times and collected a lot of mixture designs and tested them in various ways, recommended best practices, and educated state DOTs on various technologies and different things. So they're an excellent program. Check them out. They also have material database available at Info Materials. So all of their information is publicly available and very useful for concrete pavement community. So in this study, we have used their data set to evaluate what is the state of practice of paving concrete. What are we actually doing? What are we actually seeing in the field? And identify what are the opportunities for the improvement. We also wanted to identify what pavement agencies can do to save their greenhouse gases in terms of concrete pavements while preserving the performance. Here is the map of the United States, and it shows where Federal Highway Mobile Concrete Technology Center has traveled. As you can see, the map has a lot of pins. They have been left and right. They also came to Hawaii. My question was, how did you ship trailer to Hawaii? They didn't. They just shipped the equipment. Hawaii is an interesting example. We'll go back to in just a little bit. So they have 28 total main lane paving projects. So this is your bread and butter concrete. They have a few more, which were more kind of done in research capacity, but this is what your average state DOT would use on a given day. Projects are from 2011 to 2019. As you can imagine, they didn't travel much in 2020, so we couldn't like close the full decade, but we're pretty close. Keep in mind, I just want to preface that every mix design that we have analyzed is project specific and context specific. So our goal was not to say, oh, mix from Illinois is better than mix from California, because that doesn't make sense. You cannot get Illinois mix in California and vice versa. So we just want to kind of keep the finger on the pulse of paving concrete industry and see what do we have out there. We have done a life cycle assessment, LCA, in addition to the data, analyzing the data that MCTC has collected over the years. And our scope of the analysis was just cradle to gate. We focused on the mixtures while accounting for durability parameters, as we'll talk about later. This is cradle to gate scope, which is analogous to what you would get with concrete EPDs. So you have phase A1 encompassing material production of all of your material constituents, aggregate, cement, SCM, Z mixtures, and water, transportation, to concrete mixing plant, and lastly mixing the concrete, and we are doing all the analysis for 1 cubic meter of concrete mix. We also went back to see and check material sourcing with state DOTs so that we understand this phase right here, phase A2, to understand what's the effect of transportation. In this slide, I'm summarizing mixture statistics. So let's see how this works. Yes, here we go. On the top, I am summarizing cementitious material content distribution in pounds per cubic yard. And here you can see the red series here represents total cementitious content, while this lighter blue, almost invisible, shows just Portland cement. And here we have the recommended typical minimum content for slip form paving for cementitious materials. We can see that we are a little bit higher on the upper range of this interval. Also, when we analyze the paste content, here is the line of 25% paste based on AASHTO PP84. Now it's AASHTO R101. These are concrete performance-based specifications. They recommend 25% as the maximum paste content. However, most of our mixes, 17 to be exact, are actually made with over 25% paste. In terms of supplementary cementitious materials, most mixes are using SCMs, and the contents are ranging between 20 and 30%. Among our mixes, most of them are binary, meaning they have just one supplementary cementitious material. There is a few ternary mixes as well as one plain mix, and that one was from Hawaii because they don't have any SCM resources that are locally available. Finally, I am summarizing here the types of SEMs used in these mixes. As you can see, it's type F fly ash for the most part, type C fly ash, slag, as well as natural pozzolan, which was used in Nevada. Finally, we have water to cementitious ratio, ranging from 0.35 to 0.5. And this is very important for concrete durability. So we have water to cement ratio kind of spread across a broad spectrum. All in all, we have seen that due to prescriptive specifications that are largely used, most of these mixes have relatively high cementitious contents, relatively high paste contents. MCTC crew has been analyzing this trend for a long time, and they have seen some premature cracking, pretty scary photos and videos that they have shown me. So this was the trend they were observing for a long time. And here we wanted to show how it applies also from sustainability and greenhouse gas perspective. So here in this slide, I'm summarizing these box plots of 7-day compressive strength, 28-day and 56-day compressive strength of these mixes. And you can see here our typical 28-day design requirements in terms of compressive strength. You can see that on average mixes achieve these 28 design requirements on 7 days already. And at 28-day age, these requirements are exceeded by large margin. Does that mean we're killing it? We're doing an amazing job? No, it doesn't. We don't need that high strength. We don't need that much cement. These mixes are over-designed. So here we are also showing surface resistivity. Most of these mixes on 28 days fall within medium permeability and low permeability based on AASHTO, low permeability on 56th day. We'll talk more about surface resistivity in my second part of the presentation, but what I want you to bring from this one is that largely we are seeing all across the US very high compressive strengths in these paving concrete mixtures. One big reason for this are specifications, because contractors pay penalties if they don't achieve desired compressive strength on 28 days. So just to be safe, they overpowder their mixtures so that they don't have to pay for penalties. Unfortunately, these mixes have compromised durability, they cost more money, and they also have worse sustainability performance in terms of their environmental footprint. In this slide, I'm showing various correlations of global warming potential, which is the measure of greenhouse gases emitted to produce 1 cubic meter of concrete, to different mix design types. So here we have cement content, very strong linear correlation. We'll talk more about that in the next presentation, but I just want you to remember that. Very, very prominent relationship between how much cement you have in the mix and what's your global warming potential. Also, different mixes in terms of whether they are binary, ternary, what type of SCM you have. They will also fall on different parts of this line, but in general, higher cement content, higher global warming potential, no question about that. When we compare total cementitious content or even total paste content with GWP, we also have positive correlation. It's just not as strong because not all of our powdered material combinations of all of our pastes are the same. And here again, you can see this limit of 25% paste content prescribed by AASHTO PP84, and all of our mixes that have paste content above it. You can see pretty high GWP values. So in the follow-up of this work, we have tweaked and changed mix designs, optimized these 17 mixes, and we also analyzed how much carbon we can save just by doing that. We are optimizing these mix design by providing different aggregate gradations that allow for better aggregate packing and achieve the same results with lower amount of paste. Final graph here is the correlation between supplementary cementitious materials content and global warming potential. You can see negative correlation here, so higher SCM content also means lower global warming potential, and the exact trend depends on the mix design and SCM replacement percentage. This graph here shows process contributions for all of our mixture constituents and processes. So we have cement, aggregate, upstream transportation, slag, because slag needs to be ground before putting into the mix, mixing energy, and these stars here represent total GWP, which is given on secondary axis. So this slide shows us, as you can see, that gray portions of these bar graphs are very, very high, and that means that 73 to 93% contribution of GWP in concrete is only to cement, because of cement. Other noteworthy processes are also transportation, upstream transport, and slag in some cases. Aggregate is pretty low, mixing typically pretty low. I have shown you strong linear correlation between cement content and GWP. And it is true because cement is the most significant component. It has the highest contribution to footprint of concrete. But there is one more thing happening here. My LCA is following that prescribed in EPD program, so we are using only one inventory for cement. We are using industry average cement from 2020, which is the green axis here. And it doesn't give us bigger granularity to say, hey, cement from this producer or that producer. We are all just using one value for cement over the United States. And that is not ideal. So far, many cement EPDs were not available, so this trend is changing. But so far, that's how concrete PCR is prescribing that LCA should be done. But because cement is such a high contributor, there is definitely a benefit in increasing granularity of this component. In this slide, we are investigating sensitivity to cement production. And we can see that PCA's industry average from 2020 is at the bottom, and then we have higher impacts when we use PCA industry average from 2016, and yet the highest impacts when we're using this study of Marceau et al. From 2007, which was the predecessor to all these PCA studies. Overall, this is a good trend because it shows that overall cement industry is improving. So if we're using newer cement, our footprint is lower, but it's also important to increase granularity of cement data in the US because we know it's such a high contribution. In this slide, I'm investigating potential savings in our analyzed projects. If you remember, I am analyzing my 17 mixes that had potential for paste reduction between 1 and around 5% because they were over-designed. They had higher content of paste than 25%. And we can see that the more paste we reduce, obviously, more GHG reduction in percentages we will have. So the worse off you start, the more improvement potential you have, and the improvement potential by doing this can be up to 15% saving just by mix design optimization. Again, mix design optimization is achieved through improved aggregate gradation, and this is just one example where we have really sustainable solution that is extremely simple. It's not high tech, it's just an extra barrel for middle-size aggregates. And then when we translate that into total savings that we can achieve for pavement section, we are showing that here in this slide. And I have compared that just to put it in the context. So if you optimize your mix design for 1 lane mile of pavement that's 10 inches thick, you can save as much carbon as removing 27 commuters from the road for a year. Removing commuters from the road, if you have to commute to your job, is difficult. You have to find a way to get there. Maybe you don't have public transit available, you cannot bike, but changing your mix design a little bit, very easy, very doable. We know how to do that, so why aren't we doing it more? Final thing I want to mention are other environmental impact categories, not only global warming. Here we have ozone depletion, smoke creation, eutrophication, and acidification. And as we are optimizing our mix designs with paste content reduction and improving aggregate gradations, we are not only saving on GWP, all of our environmental impacts are going down. So overall, our environmental footprint is better. So these are all, this is black Pentagon represents business as usual mix, and all of these are different mixes from different states with different amount of saving relative to the baseline. So generally speaking, we are saving our financial resources, we are saving on all environmental impacts, and we are promoting durability because we don't have as much paste. And then my second half of the presentation shows correlations with durability. This is the paper that recently got published. And in this paper, we are contextualizing these embodied impacts by using mixed design parameters and performance metrics. This work has come mainly from my frustration of talking to stakeholders and often having this misperception that if we want to reduce carbon emissions of our mixes, our durability is going to go down the drain. And to investigate that, we said, okay, let's look into the data. Let's see what the data is showing. Is this fear justified, or is this just something people are saying because they're afraid to try new things, or they kind of want to kind of learn more. So many people have raised these concerns, and we wanted to do the study that investigates the correlation between mixed design parameters, embodied carbon, and then mechanical and durability properties. So to do so, we have used 4 studies. One of them I have just showed you, that's field, and that's MCTC data with 29 paving mixes. We also had FHWA Turner Fairbank, different mixed designs, and we have 2 other studies from CP Tech Center and University of Florida. Altogether, we have analyzed 145 concrete mixtures. And here you can see some other parameters. We are showing mixed types. Many of them are paving. 3 of them, in fact, are paving. 1 is structural group of mixtures. We have different plain binary ternary mixes, different types of SCMs and their replacement ranges, water to cement ratios, paste content. So we are all across the board just to see what trends are holding up. In terms of methodology, all of these studies included compressive strength test, surface resistivity test. That is kind of our proxy for durability in general. And lastly, LCA, just like I showed you in the last study to correlate everything. Okay, so in this slide, we are showing cement content versus global warming potential. This graph is kind of the dream of every researcher, very, very strong linear trend, because cement is the most significant contributor, A. B, we're all using one inventory for cement data. We need better, more granular data for cement. And we, Michelle's research group and my research group, we have done some additional work. Spoiler alert, that's coming up, but for now, this is what you have. We have shown you similar trends, and you can see these mixes with ordinary Portland cement, high cement contents, highest global warming potential, these little red dots. Portland limestone cement, that's a new thing we have included here, and you can see the line for Portland limestone cement, also strong linear correlation, but everything, GWP is lower. It's proportionally lower to that of mixes with type 1 or type 1,2 cement. And then supplementary cementitious material content over GWP. Here you can see for all of our mixes, we generally have negative trend, meaning higher SCM contents. Obviously, we have lower GWP. Compressive strength with GWP. This is where things get really interesting, because in many LCA studies, they're grouping and categorizing mixed designs based on their strength. Higher strength, higher GWP, right? No, the data shows this blob that we really didn't know what to do with. You can see here that red OPC only mixes are kind of at the top, but generally speaking, there is no rhyme or reason to this. You can achieve any compressive strength, more or less, at very different levels of GWP. You can achieve compressive strength with low, with high GWP. It doesn't have any correlation based on our data set. And these are all measured, not designed compressive strength you're hoping for. This is what lab tests have shown. I love this graph, and I owe it to Peter Taylor and their group. I call it croissant graph because they have these curved shapes, and I always like to make food analogies. So here we are showing the effect of paste content to the composed parameter that is compressive strength over global warming potential. That means how much pollution are you creating to create 1 unit of compressive strength. Higher values are better because it means you're creating high strength with minimum pollution. So, and this is only from Peter Taylor's CPTEC dataset, because they have played with paste content, we can see that these different mixes have different optimum points, but they are all around 25% or so, which coincides with AASHTO recommendation. So we know that there is the point of trade-off where you are adding more and more paste, but you're not achieving anything in terms of compressive strength, so why don't we just stop here in the middle? The next one is also the relation between surface resistivity, which is our proxy for durability, and global warming potential. Keep in mind, not for all mixes we had 56-day test. We have a lot more data for 28-day test, which you can find in the paper, but generally speaking, higher mixes with higher surface resistivity generally have lower values of GWP, whereas mixes with very low surface resistivity generally have very high GWP. This is a very important trend, and it shows us that often we can achieve durability and environmental sustainability in synergy. These two goals are not at odds. Very similar trend here for the composite parameter, that's surface resistivity over GWP, meaning how much are you polluting to create a unit of resistivity. Again, with SEM content, this number is increasing, and we can see our better performing mixes all are doing pretty well. Or all have higher SEM content, and generally speaking, have higher value of this parameter. That's kind of what characterizes them as better. This is my final slide. So based on this study, we have concluded that cement content and GWP have strong positive linear correlation. Cement is very high contributor. We need better data for cement to kind of understand exactly the levels of contribution. We couldn't find any correlation between compressive strength and GWP, but we could find that durability and relatively low GWP often go hand in hand. That gives us the idea that we can achieve multiple goals in synergy, and they don't have to be at odds. Here is the contact info. If you want to get in touch with me, I think LinkedIn at this point is the best place. But these are my Federal Highway colleagues and friends, Latoya, Migdalia, and Michelle right here. Check out FHWA Sustainable Pavements website and this new one with EPDs. Last thing I want to say, we have a session on sustainability education tomorrow at 1:30. If you want to learn more about Sustainable Pavements program and learn about how to educate stakeholders, younger, older, students, and people from the workforce on sustainability in concrete, join us tomorrow. Thanks.